Hello everyone, my name is Rob House and I am the co-CEO here at OCTOPUZ Inc. Welcome to the OCTOPUZ and Nucleo software webinar. In today's webinar, we are going to be showcasing a very powerful combination of two software solutions focusing on eliminating robot downtime for robotic welding applications. Robot downtime is a phrase that no fabrication facility wants to hear, simply because a robot that is not running is not making you money. This becomes especially true for fabricators that use robots for what we call high-mix, low-volume jobs. The two most significant contributors to robot downtime are weld fixture creation and robot programming. Coming up, you will see demonstrations of both Nucleo software and OCTOPUZ software working in unison to take care of both of these important tasks offline and away from the robot to allow for preparation of the next job well in advance.
Thanks for joining us for this presentation on Nucleo and OCTOPUZ together. We're starting the application and we're going to import a solid model of a tractor attachment, an agricultural part. So I've got a parasolid which I'll import here. We can also import 3D IGIS, and we have options for other CAD translators such as Pro Engineer, CATIA, Solid Edge, SolidWorks, etc. also. So it brings a file in. We're going to create a nice fixture for this. So a lot of these menus that we don't use, we just go straight to the fixture menu and we start the fixture Nucleo wizard. The first step is to get the part into the right orientation. So we can rotate it about X, Y, or Z, translate it, center it, align it. So what we're going to do, I'll just quickly align it to a face, get it set up to the right plane. So if I wanted it upside down, I could do this. So if it comes in at a funky angle, we can change it, but I'll put it back to the right orientation. Okay, so the next step is to set the material type. So I can select from different types of material, standard gauge material, choose 11 gauge, and it types in the nominal values for 11 gauge, 1196. You can obviously make your base plate thicker, and you also have options for some undersize or oversize in the slots. When it slots together, you need to make sure it's not too loose or too tight. You can also create your own template of favorites. You may have a 7 gauge or something that you like to use all the time, and it can remember all these values with one click. So again, you can set up like a knowledge base of your favorites. Okay, we'll go to the next step. This step is just the encapsulation, how much we're going to make the blades that encapsulate the part bigger than the component. So I'm just going to leave it at the defaults of 2 and just go next, because we can change these later anyway. This step is the base plate, how big you want the base plate to be. As you can see, you've got A and B on a picture and A and B in the dialog, so you can know which value is which. You can make it a fixed size, or you can make it like 18 by 24. You can draw your own. You can use a welding table. You can bring in your favorite welding table, or maybe a trunnion like I'll do here. You can also create a template of your favorite base plates. So you may have a Blueco table or an Acorn table where you want to use that all the time and not create a base plate, or you can create just a family of base plates you reuse with a standard pitch. So that's where you can do that. You delete that one tree. I didn't mean to actually create that. We'll go to the next one. This is where we control the Z height of the fixture, so we can make it follow the form. So the best way for this one is for me to draw some 3D sweep. So I'm going to sweep along the x-axis. Just move this out of the way, and then we can follow the instructions. So all I'm doing is sketching a kind of path we want the form to follow. So I'll just follow the general shape at the top. Try and get it somewhat symmetrical. I've got a snap grid on here, so it's quite easy. Then I'm going to do one in the opposite direction, just so I've got the width of it. You could make it a really funky form shape, but normally you just go straight across on this direction. So it's creating me one boundary there, as you can see. I might make another one, I think. So I'll sweep along the y-axis this time, just to follow that general form. Again, I'll specify its width. It's about right from there. It's about there. So now I've got two boundaries that can control my Z height. You can move, tilt, scale these. You can also do 2D ones, envelope one, line art ones. So you can draw all sorts of different boundaries. We also have the shim boundaries, so you might want to cover up holes in the part, or maybe have a shim plate. Or you can make a 0 thickness one, so it will just cover up the holes in the make a sheet body for you. Go to the next step. This step is if you wanted to do a grid, you want to do 16 parts, a gap in X, a gap in Y, 4 columns or 4 rows, for example. We can also create pins that we can extract the edges of a shape, make a cylinder for instance, and then use it to align a pin through a feature in the part through the fixture. So that's very useful if you need to maintain a critical dimension. This step we always use, we play with this every time because we need to specify the grid of lines with blade position. So he gave me an automatic size there, so I'm going to get it a bit more cleaned up to 6 inches and say generate. As you can see, it makes a grid. So this is a starting grid I can use to specify my positions. I've just hidden the boundaries for clarity. I'm just going to snap these to basically usable positions, well, more intelligent positions, I guess. What we can also do is add some lines that are user-defined lengths. So I'm going to add a few here just for extra support in places I think it needs it. So you can shrink these, extend them, and I'll show you that in a moment. So what I'll do now is I'll just select a line and move it around incrementally. Moving it up in Y. Delete ones I don't need. And really just complete the layout of my fixture positions. Next step is where we state the tab foot that goes in the base plate, so how it locks or matches up to the base plate. You can do them in the X and Y direction. I'm going to just do them in the X, and for the sake of example I'll show you this locking mechanism with a little slot on the bottom. You can see in the picture there, the bottom left. I'm going to make them 2 inches wide, and I'm going to make my slot width 0.5, and of course my height to interlock to the base plate is the base plate thickness 1196. This step here is clamping. We can import Parasolid of your favourite clamps from Carlane or Destaco. Here's some ones from Carlane that are available inside the software. Also, say, create your own clamps, pneumatic clamps, or any other solid model you have of your clamps. Next step is the bridge fixture or topside fixture. We will be releasing the Pro version summer this year. So it lets you create a fixture that also comes from the top as well as the bottom. It's good for locating small pieces inside a box, for example. So this will be coming next few months. This is weld bodies. If you draw weld bodies into your drawing, it can detect them. If they've got a naming convention, we can find, and it will warn you whether you're going to weld the part to the fixture. So the proximity of the welds to the fixture blades is checked. So this is possible too. This step is offset. You want to release some clearance between the part surface. You can do it with either a general, let's say 10 thou or 5 thou offset, or you can create these gripper points, which are these radiuses that are placed at a certain interval, 50,000th radius, every 1 inch in my case. They're good for boxes and long swept surfaces, so you can adjust your fixture and file them down if necessary, should the box or the part not be too tight in the fixture or not exactly the same as a model. This step is weight reduction, so you can make a skeletal fixture, and you can also do it on the base plate. It's good for ventilation, access with a torch, etc., and weight reduction. These are the corner reliefs in the base plate slot holes where the blades interlock. So just gives you some corner relief and some clearance. These are pin towers. So pin towers are used where you would have traditionally used a machine pin. It lets you locate something through a feature in the part sticking up in the z-axis. So if you've got a left-hand part, you need to put the left hand in the left-hand fixture. If it doesn't go up through the hole in the left-hand part, you've got the wrong part on the wrong fixture. These are the bolt holes, so 3-inch pitches or whatever you've got on your welding table. And where do you want them? On the corners, on the edge, or user-defined positions. The 17th step is the translucency and the fixture tolerances. And this is the annotation, the base plate annotation, your part number, logo potentially, and the size of the etching or the cut-through font that you use to identify the each part on the fixture so it's easy to assemble. Okay, we're done. And then we will basically build the fixture. This may take a few minutes, so we'll compress it for the sake of this presentation. But we can go back to any of these steps and change something. Like I think I need a shim boundary to shut off the blades coming through this particular piece. So you'll see now that I'm going to cover that hole up. Those holes in that part with a shim. So you can go back to any step and change anything you need. So now it's covered up. Okay, I'll build the fixture. And once it's created, we end up with a solid model. We can either directly export to DXF, or we can modify it, direct edit it and do it, and then re-export it. But what we'll get from here is a parasolid with a part and fixture that we can then take into OCTOPUZ for programming. So this is the complete fixture. I did go back and regenerate it, added a few stiffening blades on the outside, but generally it looks okay. Look at it at some different views. As you can see, if I look at it in the XZ view, you can see the tab feet that's interlocked to the base plate. So they go in, and then the whole assembly is shifted to the left to lock it down. Again, you could just have these to just be blind or just rectangular and flush to the bottom of the base plate. If I go to the YZ view, you can see the clearance between the part and the fixture we built in, which I think was 10 thousandths. We also have other options for directly editing the fixture. So I can lay it down as a 2D sketch and then do my modifications at line arc level and then put them back. We have options to add features to the edges and put holes in things, the pin projection, and also jigsaw, which is useful if you have a very big base plate or blade you need to jig up into small pieces because your laser is only a certain size. Anyway, we can export these CAD files now. We can create a Parasolid and SDL automatically, and it will create the DXFs and the bill of materials that we then take to our laser processor, along with some screenshots for the person assembling it. And the SDLs are useful for people viewing on the shop floor without a solid CAD system. So you can just use it and look at it in 3 dimensions. So this is now exporting the DXFs. We also get the bill of materials, the area and perimeter of the whole job, so you know how long it's going to take to cut and process this. This is an actual example of a very similar fixture to the one I just created for the same part, which we used at Fabtech 2018. You can see we have clamps and clamp towers included in this fixture. The part is on a rotary or a head and tail stock on a trunnion. Very rigid 3/8 material. Tack welded together. And that concludes the Nucleo part of this presentation, so I'll hand over so we can take you through the OCTOPUZ side of programming. Thanks for your time.
Okay, so I have my robot cell open in OCTOPUZ, and you can see that in this cell we have a fully kinematic rail, robot, and headstock, tailstock positioner, which we're going to use for our welds. Now the next step is to just import our geometry provided by Nucleo. So I'm going to bring in the fixture first, and I'll press import, and you can see that once it imports the model, we will have a model of our welding fixture inside our cell. So I'm just going to move it a bit closer to the robot and just quickly snap in on that. Just quickly rotate it around so it's facing the right direction. And if we want to, we can change the material. I'm going to make the fixture blue in this case. And next I'll import the part. So there's a bunch of different supported geometry types, from parasolids to step files to IGES files that will correctly import into OCTOPUZ. So we'll bring in the part next, and I'll just move it and rotate it. Next, we just need to snap those into the correct position and attach them to the rotary. So I'm going to use the align tool just to line up the center of this circular plate with the plate on my headstock. And you can see that snapped in the correct position. Close out of this, and I'm just going to attach it to my rotary. I'll do the same thing with the part. This time I'll snap this part to the origin of the fixture just because they have the same origin. Just makes it easier to line up that way. And then I'll use the attach tool just to attach it to that rotary. So now if I were to jog my rotary, the part and the fixture will move with it. Once we have this set up, we're good to start making some welds. So I'm going to go to the Weld tab and begin programming my cell. Before I do that though, I'm going to quickly make a collision detector between, let me just try that again. I had something selected by accident. So let's try making a detector between the robot and torch and the part and fixture, just so we can make sure we don't have any collisions between these two sets of objects. Before I close out of the window, I'm just going to make sure that I have my weld wire deselected so that we don't detect that feature. Give it a name. Call this one robot versus part. And then I'm good to close out of this window. Now in our program editor, we have the option to add any kind of instruction to our program. So motion instructions like point-to-points and linears. We can do subroutine calls, digital inputs and outputs, and delay statements and all sorts of things like that. So I'm going to start off by creating a new subroutine. I'm going to call this one my home routine. And I'm just going to set this up so that this will be the home position for the robot. So I'll make a quick point-to-point motion inside this routine here. And then from my main routine, I'll make sure to call that home routine at the start of my program. Now to start making some welds, we're going to open the Welding UI with this Generate Weld button. And this Welding UI gives you all the options to fully customize your weld path. So the General tab is going to give us options for the tool axis control and the kind of approach and retract motions of our welds. The Search tab will give us the option to add any kind of touch sensing or laser searching routines to our welds. We can also have stitch routines. The Robot tab allows us to define our base and tool used for the weld. So I'm just going to use base 5 and tool 5 for this weld, as well as the configuration for the robot. The Process tab gives us a couple of options to adjust our stick out, as well as our welding speed, and to apply any seam tracking or weave operations to the weld. We can also do multipass using our multipass option here. Smart Weld is our tool used for defining weld seams around any curved geometry. We're just going to use a straight geometry right now, so I'm going to leave that turned off, but I will turn on Smart Weld End to automatically pick the end surface of my weld. And there's a couple more options in the Miscellaneous tab to define the number of points in your weld if you want to limit that. You can also control the positioner and the track throughout your weld. So I'm going to go to my Stitch tab, and I'm going to make a stitch routine here. I'm going to set my spacing to 300 millimeters. You can also define the length. We'll go with 50 millimeters for the length. And you can define further properties such as your retract and approach motions between stitches. And you can even turn on even spacing if you want to. I'm going to use the ISO spacing method, which will define the distance between the start and end of each stitch. And before I close out of this menu, I'm actually going to save this recipe so I can use it again in this program. So I'll go ahead and press the save button here. Save that stitch routine as tractor_stitch. And then if I hit create, I'll begin picking my surface for the weld. So I need to define my floor surface, which I'll choose here, my wall surface, and my start surface so I can control the direction of my weld. It's going to ask me to attach my base frame. I'm going to say yes, just so that my welds move with my positioner. And then once I close out of that, we'll take a look at that weld routine. So to play my simulation, I can reset. And before I do that, I'll make sure my collision detectors are turned on. And I'll just press play to run through that routine. I can speed it up a bit if I want to. And you can see that We've got a yellow highlight there saying that we have a collision between the robot and the fixture. So if we want to see how that path, or detect any errors along that path, we can use our path analyzer tool. I'll click that. And we can define our interpolation, which is basically whether or not we want to look at individual points or also include the transition between points. So I'm going to make sure I do some interpolation with that detection. And I'll just run path analyzer for that first path. And you can see that with this reporting window, it's going to tell us how many points experience a specific error. So we have singularity, joint limits, reachability issues, as well as collision and multi-turn errors. And we have 2 points that have no errors, and the rest of them are in collision. So if we want to use Path Solver to automatically solve that path, we can just click the Solve button here. Once again, we can define our interpolation. I'll just go ahead and hit Solve for the selected path. And we'll let that run. And what Path Solver will do is automatically try to correct for any of those collision or joint limit issues throughout the path. So you can see that at the end of the solve, we have 100% good path. So I'll close out of this window, and then I'll reset and play my simulation again to see the results of that path solve. And it looks like we now have a collision-free path. So I'm just going to make a quick retract motion before doing the other side of that stitch. And to reorder any points, I can just click and drag them. So I'll put that retract motion after my weld. And I'll just slow that weld, or that speed, down to something like 250 millimeters per second so that it retracts at the end of that stitch. If I want to create the stitch on the other side, since I saved that recipe in my quick weld folder, I just have to look for it in my quick weld drop down. So you can see we have that tractor stitch recipe. If I select that from quick weld, it's going to bring me right to the part where I select my floor and wall. So I don't have to actually open up the Welding UI, I can just jump right into defining my weld surfaces. So I'll pick my floor here, my wall here, and my start at this position. Once again, Path Analyzer is going to tell us if there's any errors. So I'll run the solver again on this path. And at the end of the solve, we have 100% good path. I'll close out of this. And you can see we're now stitching the other side. So let me reset and play through the simulation. And at the end of that, I'll just retract my robot out again, put another linear move at the end of that weld. I'll turn the speed down as well. And I'm just going to create one more weld using another quick weld recipe that I have. This one utilizes smart welds to find curved surfaces, so I can actually create a weld around this curved edge here. So if I use my quick weld routine, let's use this chord weld. I'm going to select my floor, my wall. I'm going to start the weld around here and then finish on this other side over here. And then we'll use Path Solver to quickly solve any collisions with that weld. And if I close out of this, if I don't want to play through the whole simulation, I just want to look at a single weld path, I can open my schema window down here at the bottom for that weld and just quickly jog through any points in that weld path. And you can see that the robot and the positioner are working together to achieve that curved edge. And at the very end of my routine, after that weld, I'm just going to send my robot back to the home position using another subroutine call. So it goes back to the home position. So if I reset now, we'll just quickly play through our simulation. Make sure there's no collisions on the transition moves, and just look at how our welds were created. And we'll just take a look at this coordinated weld, and it looks like we do not have any collisions, so we should be good to go. Before posting out, we can change some of the parameters of our robot. So if I select my robot and I go over to the variables tab here, you can see that you can define things like your tooltip orientation. You can set your controller options. So if we want to use synchro motion on that coordinated weld there, I just have to turn on this synchro motion option. We can also define things like our mechanism name and number, as well as our welding machine used for these welds. And when we're ready to post out our code, we just have to hit the export robot code button here, and it will generate our robot code program to load on the robot. So I'll call this one tractor welds, and I'm just going to put this on my desktop. And you can see that once it's done running through the post processor, we should have a file that we can open up in any text viewer that contains all of our positions and the correct robot code for this OTC robot. And once we get to this point, we're ready to take this program and head out to the shop floor and load it up onto our robot controller.